Before we start, we're gonna just talk a little bit about like how we usually do geometry and why projective is just a better way of doing geometry. So geometry is said to be all about points, lines, and circles. Okay, you have points, you have lines, and you have circles. And what we're gonna do is just say that circles are not important for now, and we're only gonna deal with points and lines. And projective geometry is just a way of looking at these points and lines and kind of, like treating them as less as objects on the Euclidean plane and more as objects in which we can do um, sort of a lot of projective maps, kind of. So we're going to say that a lot of configurations are kind of equivalent. Like if I draw an equilateral triangle and I draw a line like this. Well, when you're dealing with projective, that's kind of actually the same as like any triangle in drawing this. So what we're inherently doing is kind of like forgetting a lot of properties exist and kind of only working with like lines, their intersections, and blah blah blah. So this gives you much more of a structure to work on geometry, but obviously also like loses out on a lot. So like this is kind of like the agenda that I want to work with. For the first three parts, I'll actually be using these slides, but for the last three, we'll just mostly be doing problems. Will mostly be interactive on the Miro. Try to keep your videos on, and if at any point any of you have questions, like you can interrupt me. You can also use the chat. I'm fine with both of them. Okay. So okay. We're gonna start by introducing the line at infinity. So your regular Euclidean plane is called R2. And R2 is just the set of points given by x comma y in Cartesian coordinates, as you all know. And for any 2 points in R2, so if you have P1 and P2, there exists a unique line passing through P1 and P2. That's the line joining them. For any two lines, let's say L1 and L2, can we say that there exists a point that lies on both of them, a unique point that lies on both of them? Is this a statement that is true?
No.
Unmute, speak up. I can see some people like nodding or anything on chat. I can have people speak up.
Like if they're parallel, then like they won't have like a common point.
Yeah. So currently we can say that for any points P1 and P2, there's a unique line passing through P1, P2. And for the rest of the thing, we're just going to call this P1, P2 with the line on top. So that's the line P1, P2. And for L1 and L2, we're going to say that there either exists a point passing through both of them. That's this point P, or the two lines are parallel. So one of those two statements is true. But this is kind of bad. So for every pair of points, there exists a unique line passing through both of them. So we would ideally want every two lines to share a unique point as well. And this is a precursor to the concept of projective duality, which we will talk about soon. But currently, we see that the statement every two lines intersect at a point except when they are parallel. That's like a kind of a bad statement. So we're going to do the most natural thing and introduce this extra point called the line at infinity for every direction. So if you have 2 points L1 and L2 with the same slope, let's say a slope of like, I know, K. And now we're going to define a point at infinity with the slope of K. So let's call it something like infinity K. And now the idea is that you have a bunch of points, which are your points in R2. So let's say this is R2 over here. And on top of that, we also have a few points at infinity. So let's say these are your points at infinity. And they kind of form a circle kind of thing, let's say. So now if I have this line and this line, this is the intersection. On the other hand, if I have two parallel lines, let's say this is your L1 and L2, then their intersection is the point at infinity over here. Yeah. And finally, we want every two lines to intersect at a point and every 2 points to have a unique line passing through them. So when I added the points at infinity, like the lines ka thing works, but we need to make sure that the points work as well. So let's say I have a point at infinity, let's say P over here, and I have some point Q over here. Does there exist a line passing? I think my net went a little bit. Till where was I audible? And more importantly, is my
You
screen showing?
you're talking about a line between a normal point and a point at infinity.
Right. Okay, so that means you guys didn't miss much. My video is lagging. This is true. My internet is just really bad. Let me try to fix that for a second and we can come back. Okay. So hopefully my video is better now. If not, just like let me know. Yeah. So I have this point P and P is an infinity and I have a point Q. What's the line passing through both of them?
The line PQ, the line at Q with slope whatever defines P.
Yeah. So I would want to draw a line PQ like this, obviously, but that's kind of weird because actually all these points at infinity are like super far away. So the slope is like, if P is defined as all the lines with this slope intersected P, then you just take the parallel from Q to that and that passes through P. So we are cooking. And finally, we have this one more thing. If you have 2 points which are both at infinity, so let's say that's here P1 and P2, we want a line passing through both P1 and P2. My internet is going again. Am I audible?
Yes, yeah.
Yes.
Okay. So the final thing I want to talk about is my video working. What is going on? Just give me a second. Okay. My screen's visible, right?
Yeah.
Okay.
Yes.
So I have 2 points at infinity. And now the point is that these points at infinity are kind of defined by slopes. So what that means is if I have a point P1, then the line passing through, every line passing through P1 is of slope S1. And every line passing through point P2 is of some slope S2. So if I want a line passing through P1 and P2, I'd want them to have like the slope S1 and S2 at the same time. How is that possible? It's not possible. Like you can't have a line with like two different slopes. So the last thing we're going to do is we're going to make this one last line called the line at infinity. And the job of this line is that it connects any points at infinity. So what we did to come up with this whole new projective system is we had our plane R2, which is your set of regular points. For every slope, we added a point at infinity. And okay, actually, slope is not the right way to put it because I think if you have a vertical line like that has an undefined slope, we added a point for that as well. So in R union infinity. And that gives you a bunch of points at infinity, which we define to be a line at infinity. And once you have that, like the setup is complete. We have a line L passing through any pair of points, which we write as P1, P2. And you have a point P, which we write as, I don't know, like L1 intersection L2. So this is just notation for two things intersecting each other. Okay. So now, like, kind of like armed with this whole setup, we can do more stuff. Okay. So I'm going to start by defining this thing called a cross ratio. Okay. Could you please repeat why we require to define the line inflation? So our entire goal in life is as follows. We want some structure of a plane such that the following two statements are true. For any pair of distinct points, you have a unique line passing through them. And for any for any pair of lines, L1, L2, you have a unique point that lies on both. And this is called a projective plane. So when we introduced the points at infinity so that like parallel lines intersect, we had an almost projective plane, which is that like the condition 2 was completely satisfied. But condition 1 was not satisfied in the sense that there was this one edge case, like you have 2 points at infinity and there was no line passing through them. So obviously we needed to fix that. And for that, what we did is we just defined this new line, a line that takes in all the points at infinity, and we are done. Now, what's special about projective stuff is that the only conditions we kind of care about are like collinearity and concurrence. So collinearity is just that P1, P2, P3 lie on the same line. And concurrence is that the three lines all pass through the same point. And we can do a lot of like projective maps or like even homographies, and we are still fine. Anyways, so through that, we have this one quantity called the cross ratio. And now I'm going to define the cross ratio, and it seems like a very stupid definition at first, but bear with me. So you have 4 points that lie on a line. And they don't need to lie in order, they can lie in any order, whatever. And you define the cross ratio as the sign ratio AC divided by BC. And then you take the ratio of that with AD divided by BD. So you have two ratios and you're taking the ratios of that, which gives you a cross ratio. And you can write this as ABCD with the commas dropped as well. That's fine. Okay, let me start with like a minor note about sign ratios. So the cross ratios have a sign, which is that AC by BC is negative if C lies between A and B. Like, okay, how do I say this? Okay, if A, C, B are collinear in this order, and it's positive, and it's greater than 0 otherwise. So we stick to the sign convention, and we have the following definition of cross ratio. Now, you don't have to remember this definition at all, because what's actually important about cross ratios is that if you have 3 points ABC, then as D moves on this line, on this projective line rather, it can also be the point at infinity, then the cross ratio ABCD is a bijection from the line to the real numbers plus infinity. Oh, nothing much has happened till now. If you're joining right now, like you haven't missed anything at all. Can you please repeat the sign convention part? Okay, that's very simple. Let's say I have 2 points A and B. Now, if M is their midpoint, what would I define AM by PM as? I would want to define AM by PM as 1, right? Because both the lengths are equal, but I'm going to define it as -1. And this is very easy. If you like see a number line or something, then I'm basically taking the quantity A minus M divided by B minus M on the number line. And since M lies between A and B, one of them is positive, one of them is negative. So the ratio is -1. A couple of facts about cross ratios, you can try to prove them yourself. Like these two are very immediate. And finally, if you have the point at infinity, so if you have A, B, C, and infinity AB just means the point at infinity along line AB. So if you have that thing, then if P is like, let's say, the point at infinity, then in fact, AP divided by BP is just taken to be 1. And this is your convention that AP is an infinite length and BP is also an infinite length. So you take the ratio and that tends to 1 as P goes to infinity. So if you have a length ratio AC by BC, you can also rewrite it as a cross ratio. Now, what's the point of all this yap about cross ratios? Like you have a random quantity over lines, and the entire point of the yap is just this one theorem. So if you have 4 points, A1, B1, C1, D1, and 4 more points that lie on lines PA1, PB1, PC1, and PD1, then this cross ratio on this following line is also equal to this cross ratio. And the proof for this is just spamming using the sign rule. So like it's very useless. You guys can try it out if you're interested and you can let me know. But this is like the one fundamental quantity that's preserved. And we say that the cross ratios are equal due to projecting from P. So we say that A1, B1, C1, D1 is equal to A to B to C to D2 by projection at P. Okay. P is not infinity. P can be any point, again, on RP2. Oh, I forgot to mention the entire plane that we created using the line of infinity is called RP2, if that is important. So you have 4 points. The setup is as follows. You have 4 points. And you can take any point P that can be outside the line. And the lines PA, PB, PC, PD, if you take any other line that also transverses it, like the two cross ratios that are formed are equal. Yeah, and like I believe the proof is just like you keep doing sign rule on like all of these. How many triangles are formed on like 12 triangles or something, and it just works out. But again, the proof is not that interesting. Now you have 4 concurrent lines. So okay, so one of the ideas that we're going to use kind of throughout this lecture is that the proof is easier than I make sound. So like I don't even know the proof myself. You need to realize that, because the only proof I've seen is like the sign rule thing, which was like one whole page. And I was like, why do I need to remember this? And the truth is you don't. Like it is just completely useless. So if you have 4 lines, let's call them LA, LB, LC, LC. Let's call them PA, P, PC, PD for now. Okay. And now if I have 4 concurrent lines.
Can you connect it? What is it called?
Sorry. Are you asking a question or are you unmuted by mistake? Okay, I will assume that that's not a question. Let's move on. If you have 4 lines and you take any line L passing through this, then no matter what the line L is, the cross ratio ABCD is invariant. And why is it invariant? It's due to this theorem that we established above. It's called perspectivity. So instead, we're just going to say that this quantity, like ABCD, is always going to be equal to some K, regardless of what line we take. We say that K is defined as the cross ratio of those lines. Okay, so again, this is like kind of like a duality kind of statement. So whatever is true for points is also true for lines, in the sense that if you have these 3 lines, then as you move the 4th point around this pencil of lines, this is called a pencil of lines, the cross ratio gives a bijection from the pencil to infinity, R union infinity rather. Okay. Okay. All cross ratios are great, but some cross ratios are like better than others. And cross ratios that are equal to -1 are like, let's say they're very good in general. Okay. So I'm gonna, okay, yeah. So we're gonna start with this theorem. Can I have a proof that if ABCD are on a line, then the cross ratio ABCD is equal to -1 if and only if ABCD is equal to ABDC? Any ideas, proofs, whatever? Can you repeat the pencil part? Okay. So a line is defined as a bunch of points that are collinear. A pencil is defined as a bunch of lines that are concurrent. That's it. So if you say this is a line L, we say that this is the pencil at P. By pencil at P, we just mean the set of lines that pass through P. It's very simple. Okay. Yeah. So we want to prove that ABCD is -1 if and only if ABCD is equal to ABDC, where these 4 points are distinct and lie on some line. How would we prove this?
If we take the ratios, we'll get that for the first one, AC by BC is divided by AD by BD. And for the second one, it's AD by BD divided by AC by BC. So essentially, they are reciprocals, which means
Okay.
only when it's equal to 1 or -1, they'll be equal. But if it's equal to 1, then C and D would be the same
Okay.
point, but it's given as pairwise distinct points.
Okay, so let's say this is K1 and you have some K2, which is A, B, D, C. So I'm gonna take this like kind of slowly, but like bear with me because I know y'all are like good enough to do this proof very easily, but um, it's good to like start from fundamentals. AC by BC. And obviously K1 times K2 is equal to 1. So essentially what this theorem is asking us to prove is that K1 equal to K2 is equivalent to K1 equal to -1. But obviously, since K1, K2 is equal to 1, we can just say that K1 equal to K2 is saying that K1 squared is equal to 1. So we finally want to prove that K1 cannot be 1, because then you have K1 squared is equal to 1. So if K1 cannot be 1, it obviously has to be -1. And the proof of that is that if K1 was equal to 1, then these ratios would be equal. But they can be equal if and only if D is equal to C. And we started off by saying that ABCD are pairwise distinct. Okay. So these 4 points are called the harmonic cross ratios. And a lot of the time when you're working with cross ratios, you will be dealing with the harmonic ones. Other cross ratios are also extremely useful, but -1 is like kind of a little more useful because it gives you that extra leeway to work with ABCD is equal to ABDC. Okay. Yeah. So now I have like 3 examples of harmonic bundles, and we're just going to prove them one by one by one. And the first one is, I think, the poster example for every single thing that you see. You have points A, B, and you have M, and let P be the point at infinity. So it's like chilling on the line at infinity over here. Can we prove that AB and P is -1? Any ideas as usual? We are trying to prove the first thing here.
AM by BM is -1 and B infinity by A infinity AB is like infinity by infinity is 1, so we
Yeah.
have minus.
So AP by BP is 1, and so that's your harmonic bundle. Okay. Buffer problems. Where did buffer problems come from? I could give you all a problem, but we will not do that for the spirit of this class. I'm also like making this class very purposefully basic, but I plan to do like much more hardcore things if you're interested in that. Let's try to put the second one. You have ABC is a triangle, and you have your internal angle bisector meeting it at D, and your external angle bisector at some point D prime. Can we prove that BCD prime is 1?
Yeah, just sine rule.
Yeah, so there are two ways to kind of go about this. One is to just do length. So like you have something like BD by DC by angle bisector theorem that's equal to AB by AC, and the other one is equal to negative AB by AC and stuff. So you're done. And what we're going to do is like deal with this more as a projective kind of sense where just a second. Okay. I've been suggested to give you all the Feuerbach problem, but that will be far more than a buffer problem. So that's not happening. We're going to project this whole system from A. And what happens is that we can think of this more as a cross ratio of lines. So instead of seeing this whole picture as B, C, D, D prime is equal to -1, we can also just think of it as you have a pair of lines, which are these lines AB and AC, and you take their internal angle bisector and external angle bisector, and you want to show that these four lines form a harmonic bundle. So harmonic bundles, I defined them earlier for points, like these points are called a harmonic bundle, but four lines with a cross ratio of -1 are also called a harmonic bundle. So how would I prove that these four things have a cross ratio of -1? Ideally, you want to like project them onto a new line or something.
Could we like take a line parallel to the external angle bisector and then say that
Yeah.
because that's one triangle isosceles triangle, and then we have the previous case, which is -1.
So if I project it into this new black line, let's call this, I don't know, B1, C1, and D1. Now I just want to prove that B1, C1, D1 and infinity is -1. And why does the last line become infinity? Because these two lines are parallel. Is infinity by infinity equal to 1 really? That's actually a very good question. The point is that AB by AC is like, it is a length ratio, but the point is that if you have 2 points B and C, you want the ratio AB by AC to be a bijection when A moves along the line. And you see that like every other quantity is achieved at some point except for 1. So we just say that when A tends to infinity, the ratio tends to 1, and that's just your definition. Back to this problem, we have these two things, internal bisector and external bisector. So when they meet at B1, C1, we notice that this thing is actually just equivalent to what we did earlier with thing number 1. So it's equal. Okay. And the final picture is the Siva-Menelaus picture. So you have a triangle ABC. Also, I think like these conventions are like meant to be questioned. So like if you have a statement like infinity B by infinity C equal to 1, well, like it's totally okay to question it because like it's kind of weird. Okay, so back to this problem, you have this, and this. And now this is like the first kind of, I think, non-trivial thing to prove that it's -1, but we can anyway take a shot at it. B, C, D, and D prime. Can we prove that B, C, D, D prime is -1? Ideas again. Again, there are two ways to do it. One is like just bash out the ratios, which we will also do. And the other is like just project. Siva and Menelaus, exactly. But we will do that proof second because the first proof is better.
Maybe you could just project ABC to an equilateral triangle.
How would we project ABC to an equilateral triangle?
Oh wait, that wouldn't really help that.
Okay. So in general, like the way projections work is like you have this thing D prime, B, D, and C prime, and you want to find like some other point in this config such that the lines like, I don't know, like some K such that KB, KC, KD, and KD prime are all kind of good lines. And in fact, I think all four choices A, F, E, and P are all just really good. So we're going to pick one of them, let's say like project from A. And we can say that B, C, D, D prime is equal to, due to projection from A, we could project onto like line EF or something, and we could say that it's equal to F E and give this point a name T D prime. So instead of proving BC DD prime is -1, we could also prove that FET D prime is -1. But that's not really extra helpful, so we can try to do more stuff, which you guys can tell me and I can do it. What's the config in the second one? It is not a config, it is just like internal external bisectors. Ideas for this one? How do we finish?
Project from P.
Yes. So we're going to project from P. And what does that give you? F is going to go to C. Okay. F goes to C. E goes to B. T goes to D and D prime. Well, D prime actually is very sad. Like it never changed. It was D prime here, D prime here, D prime here. But the point is that what we've done by these two projections is we've kind of swapped D with C. And that means due to this theorem 2 over here, that implies that BCDD prime is -1. There's another way to do this, and that is, as you said, by Siva Menelaus. So we have BD by DC times, I think, CE by EA times AF by FP is 1. This is called Siva's theorem. And you also have a dual kind of theorem, which says that since D prime E and F are collinear, so this one is equal to -1. And if I write down the same ratio with BD prime by D prime C and blah, 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 then this ratio is equal to 1. This product is equal to 1. And now if you just divide in the two equations, you'll just get that their cross ratio is -1. How did you project? I mean, this is like the same picture of perspectivity. So if you remember this picture over here, the cross ratio of A1, B1, C1, and D1 is equal to cross ratio of A to B to C to D2. And I can use that same picture in like all sorts of weird ways, right? So the cross ratio of these points, let's call them 1, 2, 3, and 4. If I project from P, I actually get like something like 1 is here now, 2 is here, 3 is here, and 4 is here. And then what we did is project back from A, and now 1 is here, but 2 is here, 3 is here, and 4 is here. So what we've done is swap B and C, which gives you your desired cross ratio of -1. Okay, this looks good. Okay, yeah. Now we're gonna work with one more thing. So till now we've only been working with points and lines. Now we're gonna work with conics as well. What's this color? Okay. So what is a conic? I will ask that question to you guys first. Any definition works.
The ratio of the locus of the point such that the ratio of distance from the of point.
Okay, so this is like it's like you take a focus and you take a directrix, and it's like the set of points such that the distance from x to p divided by the distance from x to L is equal to E. And this is, I think, kind of a convoluted like definition of conics. I think the first definition that I've ever had of conics is that conics are just equations of the form ax squared plus by squared plus, I think there are 6 possible terms that you get. And any such equation, which the thing, if you take the set of roots, that's a conic. So it's a degree 2 curve. So conics are any degree 2 curves. There are, I think, like visually ellipses, hyperbolas, parabolas, and circles are the main kind of conics. Wait, I don't get conics. Can you repeat? Bro, it's like you have an equation, ax squared plus by squared plus cxy plus dx plus ey plus f is 0. So this is an equation, and the set of points that satisfy this, set of points x comma y that satisfy this, is a degree 2 curve. So it'll look something like a circle. So for a circle, you can just use your usual definition of like x minus p squared plus y minus q squared is equal to r squared or something. And that is also an equation of this form. So this is like, let's say, one of the definitions of conic. Like say, let's definition 2. And definition 1 is like this more weird definition. I think both of these definitions are useful when it comes to doing different kinds of geometry. We will not use definition 1 or definition 2 right now. Any other definitions? I think there's also one more definition 3 that I've heard going around a lot. In fact, like there are a lot of ways to characterize conics, and in general, if you have objects with a lot of ways to characterize them, they are like good objects in general. Do any of you know any other definition for conics? As a hint, like you wanna look at the name conic. Why is it called a conic?
We take two cones, like one like this, another like this, and cut it with the plane, and
Yeah.
the thing that we get on
Yeah.
the plane of the cone, that is conic.
So we take two cones. We actually take only one cone. Like the cone just extends kind of, and it looks like this, except that it goes all the way up to infinity. Now, if you take any plane, then the intersection with this plane and this cone is a conic, which is what you would expect. Okay. But now we don't actually care about any of these three definitions. We're going to care about a fourth definition, and that is in terms of projective geometry. So let's consider like any quadrilateral ABCD. ABCD. Now, if I asked you what is the locus of P such that PABCD is harmonic or something, it seems very weird to describe, right? Like there's no way we can get a hold in this thing. And okay, so if you have this equation like PABCD equal to -1, firstly, PABCD is just shorthand for the cross ratio of the four lines PA, PB, PC, and PD. PB, PC, PD. So if you want to find the locus of P such that this thing is equal to -1, it turns out to be a very nice thing. It just turns out to be some random conic that passes through A, B, C, and D. And this is called a circumconic of ABCD. And now if you replace -1 with any real number k, you get like the locus of all conics that pass through ABCD. So in general, a conic can be determined by 4 points that lie on it and this cross ratio k. So that means that 5 points determine a unique conic. So if you have a pentagon ABCDE, then the conic determined by A, B, C, D, and lambda is the unique conic that passes through ABCDE, where lambda is the cross ratio of ABCD projected from E. So that's the kind of projective definition of conics. And we define cross ratios on conic in like the most intuitive way possible. If you have ABCD on a conic and a point P, then it's just defined as PA, PB, PB, PC, PD cross ratio, and that doesn't depend on the choice of P. Okay. You can also project from conics in this interesting way.
What do you mean by PA, PB, PC, and PD? And if you scroll on in the main.
You're not audible. Can you repeat your question, please?
In the Miro, you wrote the cross ratio of PA, PB, PC, and PD. What do you mean by that?
Right. So that's defined as the cross ratio of 4 lines. Okay. So if you're given 4 lines that are concurrent at a point, the cross ratio of those 4 lines is defined as the cross ratio ABCD, where ABCD are given by a fifth line that cuts the four lines at A, B, C, and D. But now the point is that due to perspectivity, the fifth line ka choice is my internet went again. Where was I? Anyone?
I think just defining again the cross ratio of a line of four lines.
Okay. So that defines a connect. Could I share this PDF after class? Yeah, sure. Wait, just give me a second, people. Yeah. So that's your definition of connects. And every 5 points determine a connect. So like in geometry, we say that all problems are kind of about finding coincidences. So you'll have a problem statement that says so and so, and it'll be like prove that 3 points are collinear, or prove that 3 lines are concurrent, or prove that 4 points are cyclic. I didn't share my screen. Yeah, I mean I haven't done anything on my screen for now, so it's fine. But can you see my screen now?
Yeah.
Yeah.
Okay, that should be good. All right. So it's a coincidence when 6 points lie in a conic. Why? Because a conic is determined by 5 points. So 6 points lying on a conic is like something like an olympiad problem would ask you to prove if the olympiad syllabus included conics, which it currently doesn't. But the olympiad syllabus is like kind of weird in the sense that they will give you problems that don't have the word conic in them, but the only way to solve them might be actually to introduce conics. Like I think our TSTs, like a lot of things do that. This is theorem 3, I think someone asked. So that is the definition of a conic. So what are the conditions for 6 points to lie in a conic? So if A, B, C, D, E, F are any 6 points, and I'm going to tell you, can you show whether they lie on a conic? Or does there exist some quadratic equation in X and Y such that this is a root? What's one way to do it? Only based on the things that we have done so far. Like, is there any condition that you can use to make it equivalent to A, B, C, D, E, F being conconic? Only based on the definition? Yeah, go ahead.
The cross ratio through E of ABCD and the cross ratio through F of ABCD should be equal.
Yeah, yeah. So you want this cross ratio to be equal to this cross ratio. And A, B, C, D, E, F lie in a conic if and only if these two cross ratios are equal. Okay, and there's another way to use conconicity, which is called Pascal's theorem, which is what we're going to do next. But this is kind of like the most fundamental way in which we can define conconicness. So 6 points lie in a conic if and only if the cross ratio of ABCD taken at E is equal to the cross ratio of ABCD taken at F. Okay. So now that we are given that, we will also look at alternate things that kind of are equivalent to this, but it'll take a little bit of work to prove it. Okay. So Pascal's theorem, if I put it in a very short way, it's just saying that you have a hexagon and you take the 3 intersections of opposite sides and you want to show that they are collinear. Can we take any point besides E and F? How would you want to do that?
Could you repeat the question?
Yeah, I mean, it's the question over here. In the perspectivity, yeah. So like we took the cross ratios from E and F of ABCD, but they would also lie on a conic if, say, let's take like the most arbitrary thing. Like let's say if the cross ratio from B of def was equal to the cross ratio of C from def. If this is true, they would also lie in a conic. And that's like the fundamental cool thing about conics. Like any of those cross ratio things can be true and they would lie in a conic. Uh, now to prove like Pascal's theorem, firstly, what we're going to do, and we're talking about these 6 points. If notion of like convexity or anything, sorts of like funky replacements. To make the diagram cleaner, we are going to make a very weird hexagon. Okay. Again, network went again. But hopefully you guys haven't missed much, apart from like me drawing this thingy.
Yeah, no, I think nothing other than that. It was
Okay. So you have a hexagon A, B, C, D, E, F. And I'm choosing to label it like this just to make the diagram. And now P, Q, and R are defined as the intersections of opposite sides. Okay, so opposite to that in this hexagon is DE. If you have BC, then the opposite side is EF. And similarly, for AF, you have CD. Now, if these are defined as PQ and R, you want to show that PQ are collinear if A, B, C, D, E, F lie in a conic. So seeing this problem, like any ideas, thoughts, or like, it doesn't have to be a full solution. Any idea that you feel, you can just shoot away with that. Apart from bashing. Projective and bash are like very good together, but for the purpose of this class, we will not bash.
I mean, could you do like a proof similar to that of like Pappus's theorem? Like you could prove that like the cross ratio of like with some point, like say with perspectivity at A of D, R, P, and Q is the same as the perspective at D of A, R, P,
D,
and Q.
R, P, and Q. Okay. Okay, firstly, we talked about Pappus, which we will come to like soon. Pappus is in fact just a degenerate version of Pascal. Can we use Desargues? I'm not aware of a proof of Pascal that uses Desargues. I think Pascal is kind of like Pythagoras theorem. Like everyone will just have a different proof of it. There's a very cool proof of Pascal using cubics. There's a proof of Pascal using barycentric. I think that's also a very famous one. You vary on something like triangle ACE as your reference and it works out. But for now, we'll just do like vanilla cross ratio stuff. So the first idea that we had is we want to prove that the cross ratio at A to DRPQ is equal to the cross ratio from D to ARPQ. Firstly, why would this be true? And secondly, if this is true, like how are we going to use it? Okay, so the first thing is if this is true, if the cross ratio from A to DRPQ is equal to the cross ratio from D to ARPQ, does that imply that PQ are collinear?
Yeah, like you could do like a phantom point.
And why is this? Yeah. So I think like phantom point arguments are actually, that was something I wanted to make a slide about because it's so commonly used in projective, but I was kind of lazy, so I didn't do it. And I'm going to briefly outline the idea over here. We're going to take line PQ and we're going to let it intersect AF at R1 and CD at R2. And now what do we want to prove? We want to prove that PQ are collinear, but that's also equivalent to proving that R1 is equal to R2, right? So now the point is that if AD cap PQ is another point Z, so now you have this entire picture, you have PQ and you have R1 and R2, which are so-called phantom points. We want to eventually prove that they're equal. Suppose we were able to, by some cross-ratio chase, able to prove these two cross-ratios are equal. Projecting onto this line, what does this cross-ratio become? It becomes the cross-ratio Z, R1, P and Q. This is a point C, by the way. Like, this is getting a little bit out of hand, but it should be fine. Okay. Is my screen visible now?
It is, yes.
Okay, cool. So I will just like recap what I said for like the last 1 minute. You guys might or might not have heard it. Like, I don't know how much laggy my whole internet setup is. It is quite laggy. So basically, we're going to define R1 and R2 as follows. Line PQ intersects AF at R1, CD at R2, and it intersects AD at Z. So now, the cross ratio at A from D, R, P, and Q, that's the cross ratio of lines AD, AR, AP, and AQ. That's equal to the cross ratio Z, R1, PQ. Yeah. And similarly, the cross ratio D, AR, PQ is equal to what? What cross ratio would that become?
ZR2PQ.
ZR2PQ. So now proving that PQR are collinear is the same as proving that R1 is equal to R2. And if ZR1PQ is equal to ZR2PQ, then R1 must be equal to R2 by like the fact that cross ratios are a bijection or whatever. So we just want to prove that A DRPQ is equal to D ARPQ. Now, how do we deal with that condition? Is the next question. I will also give this conic a name like gamma or something, if that helps. Ideas and stuff. A, you have okay, you have AD, AR, AP, AQ. Where do we project this? Um, so we're going to project this cross ratio to the conic, okay? And that means that's going to give me, by projecting at A, that's equal to the cross ratio of D, F, B, and E. No, okay. I need to define something called AQ cap this conic, right? So it's equal to the cross ratio of D, F, B, and Q1 on the conic gamma. But if I do the same thing with D, I'm going to get some other cross ratio. I'm going to get something like A, C, E, and P1 or Q2 or something on the same conic gamma. And that's kind of like weird. Can we do something better with this cross ratio?
Just one question.
Mhm.
Like how do you know like the cross ratio will remain the same if you project it onto a conic? Like,
Okay, so that is this theorem. Like, if you see this picture with P, A1, B1, C1, D1, and A2, B2, C2, D2, then what I'm doing over here is in fact that exact same thing.
oh, okay. Like, how would you put?
And why does it stay the same in the conic? Because that's the definition of cross ratio on a conic. So if you have 4 points A, B, C, D on a conic, like I think so far we get how to define the cross ratio of 4 points that are collinear on a line. And we also get how to define the cross ratio of 4 lines that are concurrent at a point. How do we define the cross ratio of 4 points that lie on an arbitrary conic? It's defined by taking a fifth point on the conic and looking at the cross ratio of these 4 lines, PA, PB, PC, and PD. So that is by definition the cross ratio of those 4 points in the conic. And the cool thing about conics is that whatever value K that you get, the value of K actually doesn't depend on P at all. And that's like the entire thing that makes conics so powerful when you're coming to dealing with conics. So because of that, we can just say that if AQ meets this conic again at Q1 and DQ meets this conic again at Q2, then you can say that AD, AR, AP, AQ is simply the cross ratio of D, DF, BQ1 on the conic. Okay. And if I do a similar thing with D, so let me just zoom out a bit. And I have the cross ratio of A, R, P, and Q. If I take this cross ratio at D, by projecting onto this conic, I get something like A, C, E, and Q2.
Okay, I think
On the same
projecting
conic.
through Q now is a good idea.
And what's the reason? Is there any motivation behind that?
Well, yeah, because
let's leave the right idea.
the motivation behind it is because the way you've defined Q1 and Q2, I mean, the only good thing about those two, which is in common, is the point Q.
Yeah, so you have a cross ratio and you want to project it to something, and A, B, C, D, E, F are like reasonably good points. But now you want to project like Q1 and Q2 from like P or B or something. It's not going to be that pretty. So the only points from which Q1 and Q2 are actually like good for health is Q1. So if we project this from Q1, okay, we can project this from Q1, and in fact, we can use prism lemma, which we outlined over here. That's going to give us what's the second intersection of QA with this conic. Okay, so you have ACEQ2. So the second intersection of QA with this conic is Q1. What's the second intersection of QC with the conic? It's B. And then you have E, which goes to F. And finally, you have Q2, which goes to D. So we just want to prove that Q1 B F D, this cross ratio, which is a cross ratio on the conic, gamma, is equal to the cross ratio DFBQ1. D, I think.
We are taking perspectivity about Q or that ACEQ2, right?
Yeah. Yeah. And but this simply follows from like I think the things that we did like back in the day, like these two things, ABCD is equal to CDAB. And so you just have stuff like this thing is equal to. Okay, so we want to prove that these two, but the second thing is just things. And it's also equal to Q1BDF since we're allowed to like pairwise swap things. And all of this is very intuitive because it just follows from this sign ratio kata. So that's like not even an issue for us. And if you're unclear with it, you can just ask, but it is kind of like this thing that like you can swap around cross ratios and they just work because they're defined by a ratio. My internet connection might be unstable again, so like bear with me a little bit. Okay. Anyways, that's the proof of Pascal, and that also like concludes the conic stuff, I believe. Okay. Now we're going to talk about this thing called duality. Why is prism lemma true? That's actually a really good question. I'm not aware of a proof of prism lemma like off the top of my head. In fact, I think I've done the proof at some point in my life. But when I was writing this up, I was like, okay, I need to think of a proof for prism lemma, and I couldn't come up with anything. Um, one of the proofs that I can actually do is a proof by homography, but I haven't actually taught homographies yet, so we will not be doing it. But yeah, the prism lemma is like pretty cool, and like you should definitely try to prove it.
Would we be going through homographies today?
We're going to talk about duality now. And yes, we will be going to homographies today, but I was like, we should go through homographies if time permits. And I'll do one thing. After talking about duality, I'll just like do a quick check about like of everyone, whether you're on board with everything that has been described so far. If everyone is comfortable with like everything that's been, or let's say if like 65% of people are comfortable with what's been discussed so far, we will move on to homographies. If not, then we will just like do like a reiteration of this. You guys can ask questions and I will answer. So duality is going to be the second last or last thing that we're going to cover today. Okay. The idea of projective duality is that everything that we prove about points can also be proven about lines. And so there is this thing going on called duality between points and lines. And there's also a bunch of stuff going on. So it's like if you had points A, B, and you take line AB. Well, that's kind of dual to taking if you have lines L1 and L2. It's like taking the point that lies on both L1 and L2. So the cool thing about duality is that you can actually define a bijection from the set of points in RP2. Okay, let's just call it points. Okay, so that's a set of points. We can define a bijection from the set of points to the set of lines such that incidence is preserved, collinearities are preserved, coincidences are preserved, cross ratios are preserved. And that is called like a pole-polar transformation. So because that exists, you can also kind of formalize duality. But we'll first talk about like duality in a more like informal way. So how are we going to deal with duality? Is that you have, let's say, these 4 rules or something. I think there are more rules. These are the basic ones. And every theorem or every statement that is like purely projective, that's going to have a projective dual. So we just proved Pascal, which says that if you have a hexagon and you take the intersections of opposite sides, then those 6 points are those 3 points are collinear. So now we want to define a dual theorem of Pascal, and the dual theorem is called branch, and we're going to try and like kind of define it. Okay. So going back to the statement of Pascal, let A be a hexagon gamma of duality. C, D, E, and F be points, C, D, E, and F to be lines. Statement for branching again. My zoom is okay. So how is a point lying on a conic dual to a line tangent to conic? So I think like points number 1, 2, and 3 are like very kind of intuitive. The fourth one is like a little more weird. So for that, we need to deal with what we define as the dual of a conic. Okay. So if you have a conic, it's defined as a set of points. Okay. And this thing is called a convex. Now, under duality, conics go through it, they're mapped to a thing called conic envelopes. Okay. So, like the dual of a given conic under any, like, say, polar transformation will be the envelope of another conic. And what is a conic envelope defined as? A conic envelope is just the set of lines that are tangent to a given conic. So all of these are lines. And due to that, the dual of the statement, a point lying on a conic, is that a line is tangent to a conic. Set of tangents to a conic, envelope of a conic, a lot of ways to call it. And that means that there's like a dual kind of statement that's true. So if you have 5 points, they determine a unique conic, a conic that is passing through all of them. And similarly, if you have a set of 5 lines, they determine a unique conic envelope. That means that a unique inconic, a conic that's tangent to those 5 lines. So it actually really becomes a coincidence when you have 6 lines that are tangent to conic. And it's like, I kind of like to think of it in terms of like circles, even though like the picture doesn't make sense when you're talking about it circles. It's kind of like if you have 3 points, they have a unique circumcircle. And then if you have 3 lines, they have a unique incircle. But the incircle is like not even unique because you have X circles and stuff. So we won't get into that. The point is that if you have 5 points, they have a unique conic. And if you have 5 lines, they have a unique tangent conic. And I won't go into too much detail about why it's true. So we're just going to take it as an axiom that the dual of a point lying on a conic is like a line tangent to the conic. Can you please explain duality? Do you want to like speak up and ask whatever question you have? Or is it like a full explanation? What is duality? Duality is actually like not even a mathematical term. It's like the philosophical idea that whatever has to be true for points in a projective space is also true for lines. It's the idea that whatever projective theorem you have, it also has the dual theorem. And it's the idea that can be formalized by just taking this thing called polars in a conic, which we haven't actually formally defined yet. But that's just something to keep in mind. So duality is more like just the idea that every statement that you have about a bunch of points is also like a statement that you have about a bunch of lines. And to make this clear, we're gonna like actually do duality on something. So like, remember back in the statement of Pascal, we had 6 points that lie on a conic. So now if you're in the statement of Ryan, we would want 6 lines that are tangent to some conic. So we're gonna draw a conic. And we're gonna have 6 lines. Okay. And here I call it the 6 points A, B, C, D, E, and F. So you have A, B, C, D, E, F out there. And here I'm gonna have 6 lines, and the points are not given names. The lines are given names A, B, C, D, E, and F. Is my, or is it like clear?
Whatever you said was going to be clear, wasn't clear. What exactly were you asking was clear?
Like whatever I'm speaking right now is clear, right? I think my internet is again like wavering. Like, I keep seeing your
Yeah, we can
my
see
internet
you. It's
is
just that,
slightly unstable.
yeah.
Okay. So we have these 6 lines. Now, if we go back to the statement of Pascal, we have P is equal to AB intersection with D. So when we're working over here, what is P?
The line made by the intersection, the line made by the 2 points defined as the intersection of AB, lines AB,
Yeah.
and lines DE.
Yeah. So P was defined as a point over here. So that means P is going to be defined as a line over here. So if you're going to take the dual of the statement P is equal to AB intersection DE, it's going to look like something like this. The line P, which I'll denote with a lowercase p, is equal to the intersection of A and B. So you have this point and the intersection of D and E.
What do you mean?
and you have this line.
What do you mean by the dual of a statement? Like, can you
The dual
explain?
of a statement is like you have these four duals, and if you keep replacing every point with a line, you keep replacing the line joining 2 points with an intersection of two lines, then I can use that as a set of rules to like encode a new theorem. So like when I say let A, B, C, D, E, and F be points that are lying on a conic gamma, I will instead say that let A, B, C, D, E, and F be lines that are tangent to a conic gamma. And instead of saying P is equal to AB intersection BE, I'm going to say that I'm going to take this point. I'm going to take this point, which is the line A cap the line B. And I'm going to take this point, which is line D cap line E. And I'm going to take the line joining them. And this line is called P. So previously, like P had an identity as a point. Now P has an identity as a line. And if we keep going, we will get Q as well. Q is a random line over here. And finally, R is yet another line. Now, but the final thing that was asked for us to show is that P, Q, and R are collinear. So what does that turn into over here?
We have to show that concurrent.
Yeah.
We want to show that P, Q, R are concurrent. And because of this, in fact, like the whole new statement actually has a much cleaner way of phrasing it. If we now like, and now we've done the duality stuff. So we can just like define these points as capital A, capital B, all the way to capital F. And now the statement just says that if A, B, C, D, E, F is a hexagon with an inconic, then A, D, B, E, C, F are concurrent. And I think a nice application of this is if you have a triangle ABC and you make the incircle of ABC touch the sides at D, E, and F. I want to prove that A, D, B, E, C, F are concurrent. And can we find a proof using Branca over here?
Well, yes, because
This
A,
point
F,
is the
A,
triangle
D,
center
C, E.
X11. Yeah.
Yeah, well, they are your circum. Well, those are the lines which you can take a tangent
That
to your
determine a conic.
circumconic.
Right. And the circumconic is your incircle gamma.
Exactly. Yeah.
But we kind of have a slight problem here. Like, so gamma is tangent to the lines AE, EC, CD, DB, BF, and FA, right? It's like tangent to those 6 lines. What if I defined F over here? Then this same conic, well, it's still tangent to the line BF. Like, you can see that it's still tangent. So that means if I apply Brancon, like AD, BE, and CF should still be concurrent, but that's not true. And what's the reason for that?
Because there exists no conic passing through those 3 points which are tangent to the 3 lines.
Okay, so basically we want the conic to pass through F, yeah? And this is like, I mean, it's not something that like keep coming up, but it's worth noting that if you're taking like degenerate cases where the line BF and the line AF coincide, then you will have to have F lying on the conic. Otherwise, it doesn't work because the entire thing is done by you're taking like the limit of lines BF and AF being tangent to the conic. And if lines BF and AF are like slowly converging to a single line, then F must converge to the point where the line is tangent to that conic. So that's just a minor note worth keeping in mind. It's not too much of an issue. And anyways, these concur at the center X8 if I'm not mistaken. But I forget. So this is one theorem you can prove. And now we're going to leave duality for a bit. We're going to talk about this theorem called Pappus theorem. So I talked about Pascal before, and you have 6 points that lie in a conic. And if you have a pair of lines, well, that's actually a very special kind of conic. It's a degenerate conic because it's again a degree 2 equation. Like you can take the equation of points on this line and multiply that with the equation of the points on this line, and you'll get some quadratic, and that is just supposed to be the equation of the so-called conic defined by the two lines that you see over here. So in fact, there's a statement that says that if you have a hexagon that lies on these two lines, which will look something like this, then these 3 points are collinear. And again, I can just call them A, B, C, D, E, and F. Then this PQ are collinear. Okay. It's interesting to consider what the dual of Pappus theorem might be. I have not done it myself yet, but it is something that can be. The lines don't need to be parallel; they can intersect. In projective geometry, there is no notion of parallel as such. So, like, even if they were parallel, they would intersect at some p infinity. But what is special about a point at infinity? Nothing. So, like, p infinity might as well be any point, and the lines are still cooking. Let's try to look at the dual statement of Pappus. So instead of a pair of lines, what are we going to have? We're going to have a pair of points. Okay. And we will have, instead of a point A that lies on this line. So, okay, to make the entire duality concept clear, we'll put like a purple line and a green line, kind of like the metro lines in Bangalore. And you will have a purple point and a green point here. So instead of a point A that lies on the purple line, we're going to have a line A that passes through the purple point. And we'll have line C, E, and line B, D, F. So now what does the statement for Pappus look like over here? So that's C, D, E, and F. So I think I'm not drawing it in the best way possible. I think there might be a better way to define this stuff. But what it's basically telling you is that, let's make this line better. If you have lines, yeah, okay. Just bear with me while I just fix the labeling and all that. This is E, this is D, and this is F. Then the new statement of Pascal is gonna, the new statement of Pappus is gonna say that if I take the line joining these 2 points, let's give them a color, the 2 blue points, and now the next one is BC cap EF. So I'm basically gonna take the intersection of B and E and take the intersection of B, E, and F over here. And finally, I'm gonna take the line joining the intersection of A and CD and FA. So F and A are going to intersect in some faraway place. Let's say over here. FA. Then it's saying that the blue line, the green line, and the purple line are concurrent. Hopefully that's clear from the picture. This is a horrible picture, but that's fine. So that's duality for you. Like when we took the dual of Pascal, it gave you this very cute theorem. It gave you that if you have a hexagon with an inconic, then these 3 things concur. But when we had this, when we did it for Pappus, we got a very weird theorem. Maybe if we draw the picture in a better way, it might turn out to be something good, but we'll never know. And in general, like whenever you have a statement that's purely projective, it's always worth considering what the dual statement is going to be. So for some theorems, the dual statements are like very weird, like they don't make sense at all. For some other statements, the dual is in fact kind of better than the original statement itself. So there's this theorem called DIT for involutions, but if you take the dual, you get a theorem called DDIT, which is like just infinitely better. Can we directly cite duality during a contest? What would you want to cite is the question. Can we take the dual of a theorem and prove? Yeah, I mean, I think I have done this. I've cited duality on APMO, I think, and they didn't like dock any marks for me. So like, hopefully that's possible. Yeah, and how you're going to say it is you're going to say that this theorem is true because it's the dual of this famous theorem. So I actually did this for Broca's theorem. I said that if you have an encircle so and so thing is true, because this is just the dual statement of Broca's theorem, so you're done. Okay, so till now we're going to like take a quick kind of refresher. How many of you here can I have a show of hands if you're like completely confident about all of this? And I think for most of you, that might be because you guys have just seen this before. Like everything I've said, if you've done a class in Projective Geo, you've probably seen all this before. For many of you, otherwise, who I'm actually hoping to like cater to, you guys are seeing this for the first time. So in that case, like again, show of hands if you guys are thorough with it, and if you're not, we can just go through and have some questions again. But for now, I'm going to take it on face value that all of you are like cooking, that all of you are comfortable with everything. You guys might be getting peer pressure, in which case, please DM me and I'll be happy to explain everything. But we're going to talk about homographies now. So
Just one thing, I wanted to like look at the dual of Papus again. I'm a bit confused
the
about
dual of Papus again. Yeah, even I'm confused about that. It
Okay.
says that you have these three lines that are concurrent.
Oh wait, I don't
And
think you're sharing your screen.
oh, I'm not sharing my screen. Okay, I haven't done anything on my screen. That's fine.
Right.
I was fixing this poll up. Yeah. The dual of Papus, I mean, it looked like it might be good, but I don't think I have a picture that like fully shows why it's good. So
Yeah,
the dual of
because
Papus tells you that if you have these concurrent lines, then the line joining the blue things, the line joining the green things, and the purple things are concurrent.
yeah,
But
because like
weird
what
symbol.
I was concerned with is I wanted to like when we were doing the dual of Pascal and we saw that it was Brankin, we first did all the duality thing and then we redefined looking at the figure we had. I wanted to do that
True.
here. Like I wanted to see this because I couldn't really get it
So
either.
currently this picture is very weird, but if we actually draw the lines A, B, C, D, E, F in a much more nicer way, we might end up getting a picture that's actually workable with. Like this one looks very stupid. If you find a picture like that, let me know and we will actually do it.
Right.
So homographies. Now, what I want you all to notice is that everything that we did in this entire Miro till now, we proved Pascal and we just talked a bunch. I mean, we proved the Siva Menelaus picture. We proved all this. All of that, we actually never used the shape of the triangle, kind of. All we did was just like project, and like, or maybe just take like a line intersected with another line. We've never used the kind of shape of things. And what homographies are gonna help you do is actually they're gonna help you use the shape of things in a very weird sense. Okay. So what is a homography firstly? So I wanted to start by talking about like projective maps and like how they preserve cross ratio and stuff, but we're just gonna go straight into it. And this homography section is gonna be very short and very weird in the sense I may not be like explaining everything fully and just hand waving a bit, but like just bear with me. Screen freeze, yes. My thing went again. It's becoming common occurrence now. So on the left side, like I've written a bunch of homographies we can do on RP2, and that will be sitting there for a while. And meanwhile, I'm just going to be writing down a problem over here. If you have any questions like about anything, you can ask me again. So okay, I'm going to write down a very beautiful problem over here, and we're going to try and solve it.
Will we do any problems after the theory?
I don't think we have the time. I had a couple of rounds in mind, and that's actually very sad because like you can't say you've learned the whole thing fully unless we've done some problems with it. But unfortunately, we're not going to have the time today. So what I'll do is I'll do another projective class, which is more of a PSS kind of thing. So it'll just be a problem solving section. Like this class has been a very theory heavy kind of section. So like I just like introduce cross ratios and stuff. So we haven't got like the bandwidth to do any problems beyond the one that I will be doing right now. What I also will do is for those of you know MC, I can give you like a bunch of problems that can be solved using homographies or vanilla cross ratios. And you're welcome to try them and like DM me with any progress you have or any hints you want.
For like x1 and like y1, like wouldn't like x1 be like PR intersection like CD because like P lies
Because
on
of
A.
symmetry,
And, like P
I
like
think it defined PP wrongly. So I think P and Q have swapped definitions. So it's like my skill issue. And Q is equal to AD cap BC. Yeah. So now the definition should be reading right now. Hopefully, yeah. This looks good. PR cap BC. Okay. So now I want to prove that. Okay, so I think my screen looks like kind of grainy-ish now, but hopefully you should be able to get a gist of it. So this is a problem in all its glory, and like I wanted to actually like write it down as we're speaking to like kind of see what's going on. So any ideas on how we can do this?
You don't by chance already have a diagram of this on you?
Huh? I don't. And what I did is I wanted to actually like write down this entire problem step by step, so that we can like see how like absolutely gory it is, and like what's the solution for this going to be? Like, can we bash it out? Maybe can we complex fashion ABCD? Like everything that you try like looks very bad here, except for I think barycentric is not too bad because like everything is just lines and intersections. But when you see a problem like this, where everything is just a line cap a line or a point and or a line joining 2 points, it's telling you that the statement is purely projective, and that means we have a very amazing nuke that we can do, and that is called homographies. Okay, so here's the idea of homographies. So your step one will be like you have a random problem, so and so. Now step two is going to be like we're going to use one of these three things. We're going to use one of these three homographies, and we're going to apply that homography to everything in the problem statement of once. So let's say you have this problem thing, and then you're just going to like apply a projective transformation to the problem. So we're just going to homography P problem. Okay. And now we're going to solve the homography problem, which is hopefully easier to solve. And then we're going to solve this. And what we're going to do is we're going to homography things back because a projective transformation is injective. So if we homography back the solution, we've suddenly just got a solution to this entire problem. Am I audible what I'm saying? Because my Miro is like cooked.
Yes, yeah, you're audible. When you said you're taking another homography, does that mean that you're going to take every step of the you're taking and take a homography of that?
Wait, Ronas, can you repeat your question because my internet died?
Yeah, so like the fourth thing you said was that you take another homography back. So you suddenly get a solution which works for the original problem.
Yeah. Yeah.
But does that involve homographying every single step? Like you have a statement, you have a step in your solution, and then you're saying that, okay, its equivalent is this thing. Or is it something like when you do inversion? Like you say, okay, this is the inverted problem, I've solved it, you can invert back. I'm not going to say what every single step in the inverted solution, inverted back is, but it works.
Exactly. Exactly. And it's like the second thing. You're going to say that it works because I can invert back, but I'm not actually going to invert back the entire statement. Bro, my video is freezing again. 1 second. Okay, hopefully I'm audible now.
Yeah.
Hello. Hello, can you hear me?
Yeah.
Okay. My internet is really unfortunate today. Yeah. So when we do the fourth step where we homography back, we're not actually going to homography back the every step that we did for the solution because that may not even be possible firstly. So when we're doing this step 3 of like solving the problem, we will actually use non-projective stuff. We can use angle chase, we can use like we can use stuff like lengths or like anything, or even like trig bash that's just not projective. And when we're doing that solving, we're doing non-projective stuff on a very simple problem. But the point is that in the problem statement, everything was defined projectively, and the condition that we had to prove was also projective. What is a projective condition? Something like 3 lines, 3-point circle in your 3 lines are concurrent. Or you get the idea, or like 6 points are coconic or something. And because of that, because everything is projective, and we've proven that a given set of projective conditions implies a projective statement, we can and will homography things back. So now looking at this problem, it's like this beautiful thing with a bunch of intersections. But what I claim is that there exists a projective transformation that takes any quadrilateral ABCD to a square. And why a square? Because like squares are just nice to work with. And what that means is that if I solve this problem in the case where ABCD is a square, then I've solved the problem for any quadrilateral ABCD. So now we're obviously just going to do that. We're going to take a square ABCD. And what does P become?
Point at infinity along AB.
In fact, I can just let you guys solve. Yeah. So P is far away. It's here. Let's just, like give the line at infinity over here for convenience. Like, it's just existing over here. Okay. So this is P. What is Q?
ED inside. Okay, yeah. Point of infinity along DA or AD, whatever it is.
Finally, we have R.
E.
R is the center of the square. Now you have x1 is equal to PR cap AD. What is line PR? It's just the parallel line through R. So x1 is just the midpoint over here. What is y1? PR cap BC. That's over here. What are x2 and y2?
Yeah, the
It's
midpoint.
QR cap AB, which is over here. Okay, now I have to like again do some copium over here because I seem to have written the problem statement wrong. You're gonna prove that x1, x2, y1, y2, and pq are concurrent. Because as said, the statement would give you that x1, x2 cap y1, y2 is R, which is obviously not true. Anyways, you have x2 and y2. And just rewrite this properly. You want to prove that lines x and pq are concurrent. What is line pq? P is a point at infinity and Q is a point at infinity. So it's just a line at infinity. And so that's basically saying that we want x1, x2, intersection y1, y2 to lie on the line at infinity. In other words, we just want x1, x2 to be parallel to y1, y2. And this is like just proof by obviousness. Just look at the square, they're parallel, so you're done. GG. Another cool thing is that we prove that three things are concurrent when ABCD is a square. But due to like this rule number 1 of homography, we can say that because we proved it for this specific configuration of ABCD, it's true for all quadrilaterals by projective transformations, and you're done. So that kind of concludes what I wanted to give a gist of homography. I had a bunch of like kind of buffer problems that you can also do using homography, but it's much more complicated. Like in this one, we just doing like a straight transformation to a square and you're just done. In some other problems, it's not as simple because like there might be a random circle going on, or you want to prove that two lines are parallel. And how do you translate such a Euclidean condition to a projective one? Well, what you do is you find a third line that's parallel and you say that, oh, I just want to prove that these three things are concurrent or something. So the general idea of homography is to take a problem and there's this intermediate step, let's call it step 1.5, where you're going to translate the problem from Euclidean to projective. So the reason it's kind of step 1.5 is because for this beautiful problem, there was no translation. It's just everything is completely projective, projective, projective. On the other hand, you'll encounter a lot of problems that are like 90% projective. So like for that last 10%, we will have to do kind of some translation, then we will be done. Will there be extra problems for this in the P set? I mean, I think most of the problems that I will give will end up being like some form of homography because everything else we've learned in this class is more like theory building rather than actual problem solving techniques, apart from maybe like projecting cross ratios a bit. So I think that concludes what I had to say. Any questions? Anything else before I stop the recording?
Are those four the only homographies? I mean, how many are there? Is it just random? Or...
How many are there? So a homography is like characterized by multiplying by a matrix. In fact, I can characterize homographies in a very clean way. If you have a plane, then a homography is basically, and that plane is RP2. So that plane is like the Euclidean plane plus a line infinity.
Yeah.
A homography is defined as any function from RP2 to RP2 such that collinearity is preserved. This is called a collineation, and you can prove that every collineation is actually multiplication by a matrix in homogeneous coordinates. So that's like the more like gory algebra part of it, which we won't get into. But what it's basically saying is that if I have a plane over here, then every homography can be defined as taking a point outside that plane and projecting the entire plane onto this new thing.
Wait,
So
you
that's a
have the
homography for
plane,
you.
you have the plane, you
Yes.
have that point, and then?
And then you're going to project everything from that point. onto a new
Right.
plane. It's like how
Right.
you're doing perspectivity.
Yeah.
It's like perspectivity on lines except with planes. I could share my screen again and show you, but like the internet stuff is cooked. So it's like perspectivity except like you're kind of projecting in 3D. So every homography can be characterized by that. And I think the strongest characterization is that you can take any quadrilateral to another quadrilateral. Now, some properties of homographies are that I just defined it as a bijection that preserves collinearities. But it so happens that every such function also just preserves cross ratio. Every such function also preserves conics. If you take a conic, then the new thing will also be a conic. So all these things are actually not apparent. Like I said that there's a bijection that takes lines to lines. Why does it have to take conics to conics? That's not apparent at all. But like it just so happens that because of how the algebra works out, you can characterize homography so cleanly. And the three things that I said are, I believe, not the only things. Those three are the things that you will use in contest, and mostly those three are the only things that you will ever need usually for the purposes of homographies for now.
Right.
Eventually, there's also one more thing where you'll do homographies on CP2 instead of RP2, but that's probably for another lecture with like circle points and stuff.
How did you get like the three lines to be concurrent, in the end?
In the last problem,
Yeah.
so you had a picture where x1, x2 was like the midpoints of these sides, and y1, y2 were also the midpoints. And
the
what you wanted
opposites.
was that, you wanted that x1, x2 and y1, y2 meet on line PQ. But then line PQ is just a line at infinity because P and Q,
Yeah.
like, like infinity is over there.
Yeah.
So what does that mean? If you want two lines to concur on the line at infinity, you just want those two lines to be parallel.
Yeah.
And if you have a square and you have midpoint, 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 then these things are parallel. The midpoints form a smallest square, so you're done.
But
yeah,
x1, y1, and x2, y2 actually concur R.
They meet at R. Like I mistyped the problem. It is you want to prove that x1, x2, y1, y2, and pq are concurrent. Yeah, otherwise it makes no sense, right? Like you want to prove that p, r, q are collinear, which is like just not true. Any other questions?
Okay, just a pedantic point. So like when you're adding the line at infinity to the Euclidean plane, you're not really defining the slope for it because you can't.
Yeah. So line at infinity, you can't actually define it using Cartesian.
Yeah.
In fact, the best way to define the line at infinity is this thing called homogeneous coordinates. You have the Cartesian coordinate system where every point is assigned a coordinate x, y.
Okay.
Now we're going to make a coordinate system where every point is assigned 3 coordinates instead of 2 coordinates. So we're going to assign it x, y, z. And the idea is that x, y, z maps to the same as kx, ky, kz for any real parameter k. And this is called a homogeneous coordinate system. And how we would make the bijection is by taking
then is there a bijection of that with the 3D space since we're having 3 coordinates?
Yeah. So that is precisely what we're going to come to. Okay, this if I want to talk about. Okay, what I will do is I will stop recording and we will conclude this class, and then I can talk about homogeneous coordinates for a bit for whoever is interested. So for now, for our purposes, the class is